right, so today we're going to start Chapter 10. Okay, Chapter 10 is basically on solving systems. We'll do a quick review of how you solve basic systems with 2 variables, 2 equations. We'll get into 3 and 3. Okay. And then I'll show you kind of a quick introduction to a matrix, which is a more efficient way to write things down, so you don't have to write as much, but it uses the same steps you already know, just less writing. And maybe we'll finish up if we have some time solving some nonlinear systems. More complicated nonlinear systems. Okay, so first definition of a system. Basically, you're solving 2 equations, 2 or more equations for 2 or more variables. In general, if you have 5 equations, you want 5 letters in those equations. Okay? So if the number of letters matches the number of equations and all the equations are independent of each other, usually things work out nice. Okay? If you start to run into situations where you have more equations than you do letters, or the other way around, things can get a little tricky. You can have what's called an overdetermined system, meaning there is no solution to it. You could also have infinitely many solutions. Okay, these kind of things can happen. All right, so first problem, I just want to set this up. We're going to come back and solve it a little later. But I'm giving you 2 facts about a rectangle. The perimeter is 100, the area is 300. We're going to find the length and the width. Okay, anybody think they could give me one of the equations you would set up here? One of the equations will have to do with perimeter. The other one's going to have to do with area. And maybe before you give me the equation, might be a good idea to pick some variables. Okay, I think with what they're asking for in the problem, the letters we're going to use are almost common sense here. Okay, so what variables do you think we should use here? Obviously.
X.
Okay, X.
Y.
All right, we could do X and Y, which would make good sense if we're going to graph it. Okay, if you're going to graph X and Y, perfect. How about if we're finding length and width? What's an even easier letters to remember which one's which? James?
L and W.
Yeah, could use L and W, but X and Y is fine as well. Okay, I'm gonna do L and W. Anybody give me one equation that I would set up here? Yep, Darren?
2L plus 2W.
Good. 2L plus 2W equals 100. That's the equation for the perimeter. Twice the length plus twice the width equals 100. How about the equation using the area? James?
Length times width.
Right. Okay. Something to kind of look at quickly. First equation is linear. The second one is not. Okay. If you were to use x's and y's like we said before, you could solve the top equation. It would be y equals mx plus b form. The bottom one isn't. When you have a product of variables equal to a constant, this particular one is actually a hyperbola. It's not a hyperbola the way we've seen it, though, with the transverse axis going vertical or horizontal. The transverse axis is actually on a 45-degree angle. It's a hyperbola that would look something like this. The 2 branches would be in quadrants 1 and 3. Okay, but we're going to focus on solving things algebraically, so probably not going to graph this one. Okay, the 2 algebraic methods we're going to use are substitution and elimination. Okay, as I put them up on the board, if you already know how to do substitution and elimination, you don't need to write down the directions. Okay, it's the same substitution and elimination you learned in Algebra 1. We're just going to go through it real quick, make sure everybody remembers it, and get on to some harder kinds of problems. Okay, it's basically 3 steps with substitution. Take one of your equations and solve it for one of its variables. Okay, so pick an equation, solve it for its variable. Take what you just solved for and plug that into the other equation. Okay, once you simplify it, you should know one of your variables. So in our case, if you're solving for length and width, after step 2, you're going to know one of those things, either the length or the width. Once you figure out one of them, take that answer, you're going to plug it back into one of the original equations, and then get the other variable. Okay, so those are the basic steps with substitution. So let's kind of compare these steps to how we would do the problem we just had. I'm going to stick with L's and W's. All right, first thing, pick an equation, solve it for a variable. Which equation there is easier to isolate one of the variables, the top one or the bottom one? James? Yeah, the bottom one. You can do it in one step. Can you tell me what I could do to get something by itself?
Divide by W.
Sure, divide by W. Now L is 300 divided by W. Take that result and plug it into the other equation. Okay, so I'm going to take 2L plus 2W, fill in what we just got for L. So I have 2 times 300 over W plus 2W equals 100. Okay, next step, multiply 2 times 300. Don't multiply 2 times W. If you want to think of the denominator, it's a 1. So it's 600 over W. What's my next step? What do we do next there? Darren?
Multiply W.
Yeah, multiply what by W?
Each side.
Yeah, multiply each side by W. Now, because we're going to multiply each side by a letter, we have to check for extraneous answers. By multiplying each side by W, we might be introducing a new answer here that isn't an answer to the original problem. Okay, so now we've got 600 plus 2W squared equals 100W. Okay, what kind of equation is that? Oh, Victoria? Think back to Algebra 1. What kind of equation is that? It's not written in the order we normally write it in, but what's your highest exponent there? 2. So what does that tell you? It's a blank equation, quadratic. That's a quadratic equation. So now we have to figure out how we solve a quadratic. If you're trying to solve a quadratic, what's your first step? Yep.
Everything on one side.
Get everything on one side. So you're going to get 0 on, I would put 0 on the right. I would also put the left-hand side in descending order. Highest exponent down to your constant. So you get 2W squared minus 100W plus 600. Now, even before you try to think of the different methods you can use to solve that, there's something you could do to make the numbers a little smaller in this equation. Anybody see what you could do to all four parts? Yep.
I was going to say divide by 2.
Yeah, you can divide everything by 2. Okay? Just going to make the numbers a little smaller. So W squared minus 50W plus 300 equals 0. Okay, I'm going to give you a hint. That's not factorable. So if you were thinking maybe I can factor that, you can try. It's not going to work. Okay, so besides factoring, what's Emily? What's another method we can use to solve? Yeah, we could use the quadratic formula, or we could complete the square. We've been doing a lot of completing the square lately. Let's do the quadratic formula, though. We haven't practiced that quite as much. Okay, so Alex, what's A, B, and C?
B 150 and 3. No.
A is what?
1.
Yep.
50. No, negative 50.
Negative 50.
300.
300. Good. Now we'll fill that into the quadratic formula and solve. Okay, keep in mind what kind of answer we're solving for. We're solving for a width. Width should always be a positive number. So if we get a negative, that would be an answer we cross out. Maybe we will, maybe we won't. Okay, so we get negative b plus or minus the square root of b squared minus 4 times a times c. 4 times a is 4. 4 times 300 is 1,200. Okay, all over 2a. Okay, next I'm going to take the square root of 1,300. Okay, just get that as a decimal. Okay, 36 point, I'm going to go to 3 decimals, 056. Am I going to get a negative answer when I do the plus or the minus here? Cody?
No.
Nope. I'm not going to get a negative either way. So let's write down both and see what happens. We've got 50 plus 36.056 divided by 2. So one answer we get is 43.028. Okay, other answer we get 50 minus 36.056 divided by 2, 6.972. Now remember, we're finding the width and length. There probably should only be one answer here. Okay, well, let's see what happens when we find the length. Okay, now that I know the width, let's start with 43.028. Kelsey, how can I get the length?
If you plug that into one of the original equations.
Yeah, I could go all the way back to one of the originals, or do I have an equation that has L by itself?
The L equals 300 over W.
Yeah, so the length is 300 divided by W. So let's just do that. Let's do 300 divided by W. 6.972. Okay. Any guess what the other length is probably going to come out to? Darren?
43.
Yeah, it's going to come out to 43.028. Wait, so I'll just show you. Take 300, divide by 6.972. Okay, this comes out to 43.029 because of the rounding, but basically the same thing. Okay, so I guess technically we get 2 different solutions here, but are these really different rectangles? I guess it just depends on which way you're looking at it. Okay, it's basically taking the rectangle and turning it. I think generally when we talk about length and width, we let length be the longer dimension, and we let width be the shorter. But in this case, technically there are 2 answers, it's just one's rotated. Okay, questions on that? So there's your width and your length. So this is a nonlinear system. Okay. Basically just found where a hyperbola crossed a line. You get 2 answers. Okay, this is a linear system. Okay, so looking at that, we want to try to figure out which equation would be easier to solve for a variable. Casey, which one do you think is easier to get a variable by itself? Yep. First one, which variable you want to get by itself?
One.
Yeah, I would get y by itself because it has a coefficient of 1. Anything that already has a coefficient of 1 should be easy to get by itself. Can you tell me, Casey, what would y be?
Negative 2x plus 5.
Yep, perfect. I mean, she wrote it in y equals mx plus b form, which definitely is a great way to do it if we're going to graph. You could have also written 5 minus 2x, but what you said, that's perfect. Okay, so y is negative 2x plus 5, and fill that in. Okay, Colby, what's my first step here?
Distribute 2.
Yep, distribute out the 2. So, all right, so we're going to get negative 4x plus 10. Brianna, what's 3x minus 4x? Yep, and negative 1x. I'll bring the 10 to the other side. And Cole, what do we get for x? 8. Good. Okay, now that we know x is 8, what we'll do, take and plug it back into the equation where we already had y by itself. See what we get for y. I'm going to have negative 2 times 8 plus 5. So we get negative 16 plus 5. Andy, what's negative 16 plus 5?
21.
If it was positive 16 plus 5, it would be 21.
11. Negative 11.
Negative 11. Okay, you might see this written as a coordinate too. Generally, when we talk about graphing, the teacher will ask you to write it as a location, or you can write it just the way I did. Either way. Okay. Questions on that? Okay, so again, this is the location where these two lines would cross if you drew them. All right, let's take a look at elimination. Okay, so elimination is a little bit different method to solve. Okay, it works well when you have linear systems and you have everything lined up in columns. Okay, so the idea is that you're going to add a linear combination, or basically a multiple, of one equation to a linear combination or a multiple of another equation to try to get variables to cancel out. Okay, generally, the way I do it is I try to make sure the coefficients are opposites. You can really do it either way. If they're opposites, we're going to add the equations together and something will cancel. If we got them to be the same, we would subtract and something would cancel. Right. But I would really just try to make sure they're opposites. So the way we're going to do that is you're going to multiply everything in an equation by a constant. Sometimes you have to multiply both equations. It depends. The constant, try to pick an integer. Try to avoid fractions and decimals. That's going to make the arithmetic somewhat hard to do in our head. Okay, so here's one that's set up pretty well to do elimination. You have two linear systems. The x's are lined up, the y's are lined up, the constants are on the other side. So first thing we have to decide is, are we going to try to make the x's cancel out, or are we going to make the y's cancel out? Okay. Generally, the way I do that is I try to figure out how can I do it and keep my numbers as small as possible. All right, so if you look at the coefficient of x's, you have a 2 and a negative 3. You're trying to think of a number that both 2 and negative 3 divide into without a remainder, if you want to get rid of the x's. If you want to get rid of the y's, you've got a 3 and a 5. You're trying to think of a number that both 3 and 5 divide into without remainder. Okay, so which variable do we want to try to get rid of? The x's or the y's? What, Jill?
X.
Yeah, if we get rid of the x's, what number do 2 and 3 both divide into? 6. So we want to make one of those a 6 and one of them a negative 6. Let's call this one equation 1. This is equation 2. What could we do to equation 1 to make that first number, coefficient of x, a 6? Darren?
Multiply by 3.
Yeah. So let's take 3 times equation 1. Okay, this notation that I'm using, I'm going to start using when we do this, especially when we use matrices. Anything that's circled and it's a number, that represents an equation. So I'm saying 3 times equation 1. Okay, let's do that out. So that's going to give me 6x plus 9y equals 15. Okay, what could I multiply equation 2 by? James?
2.
Yeah. We're going to take 2 times the second equation. That's going to give me negative 6x plus 10y equals 42. Now add your equations up. Brianna, what's 9y plus 10y? 19y. Okay, 15 and 42 gives me 57. Last step, divide by 19. Okay, y is 3. Okay, Alex, what else do I still have to do? I'm only half done.
Find x.
Yeah, we still have to find x. So I'd pick one of the original equations, take y, plug it back in. I'd say this time probably the top equation. The numbers are all smaller, and there's no negatives. Okay, so you get 2x plus 3 times 3 is 9 equals 5. Okay, bring the 9 to the other side. 5 minus 9 is negative 4, and divide by 2. So y is 3, x is negative 2. Okay, so that approach we just did, that's elimination. Any questions on that? Any questions on that notation that I'm using? Circled numbers, that kind of stuff. Circled numbers represent equations. Okay. So again, we just found where these two lines cross. They cross each other at the point negative 2, 3. So we got one solution. What's another situation that could happen when you draw two lines? Instead of them crossing in exactly one spot, they could do what? Darren?
Be the same line.
They could be the same line. Okay. What else could happen? They could be the same line, they could cross at one point, or, yep,
They could be parallel.
they could be parallel. Well, if they're parallel, they never cross, there's no solution. If they're the same line, they cross infinitely many times. So those are the three cases you can have. The lines cross once, they're the same line, so there's infinitely many solutions, or they're parallel. No solution. Okay. Again, these are only the cases for two lines. If you start talking about more complex shapes like ellipses intersecting with parabolas, you got 5 different cases there. 0 through 4 solutions. Okay, but for lines, there's only 3. Right, so this one I'll let you decide if we should try substitution or elimination. Cody, what method do you think would be the best for this problem?
Well, substitution.
Okay, do you have any variables here that have a coefficient of 1? No. Yeah, I'm not saying you couldn't do substitution. You definitely could. But I think elimination is going to be faster. You're basically going to do one thing with elimination, and then you'll know your answer. Substitution here, I think, would get into some messy fractions and stuff. All right. So since the x's are lined up, the y's are lined up, constants are lined up, I'd use substitution. In fact, we're only going to have to multiply, elimination. We're only going to multiply one equation here. You want to see what you could multiply the top equation by? Yep. 3. Okay. So let's find 3 times the first equation. It's going to give me 6x minus 3y minus 9y equals 15. Keep the bottom the same. If you want to put something down, we're just going to write equation 2. Not going to do anything to it. So negative 6x plus 9y equals 10. Now add those equations up. Okay, how about Casey? What's 6x minus 6x?
0.
That's gone. How about negative 9y plus 9y? 0. So now we've got 0 plus 0 on the left. We've got 25 on the right. Once you reach a point where all the variables are gone and all you have is a number equals a number, you're done. We have to interpret what this means. What does that mean? 0 equals 25. Yep. There's no solution. This is a false statement. The answer is not false. The answer is no solution. Okay, so if you were to draw these lines, they would have the same slope, different y-intercepts. They're parallel. Okay, let's look at this one. Okay, Andy, what method could we do here?
Substitution.
Okay, you could do substitution. Probably solving that top equation for x would be the fastest way to do substitution. But I think elimination is going to be even faster again. But again, you could do substitution. Did anybody see what equation I could multiply by something? And actually, that's going to be my only step, and then I'm going to be pretty much done. Yep. Yeah, multiply the top by 2. So let's take 2 times the first equation. Don't do anything to the second one. Keep it the same. Well, look what happens here. 2x minus 2x, 0. Negative 6y plus 6y, 0. Negative 4 plus 4, 0. Again, I told you, once you reach the point where your variables are gone, if you have a number equals a number, you're done. We have to interpret what this means. James, what does that mean?
That's true.
Okay, it is true, so what's my answer?
One solution.
No, not one solution. If it was one solution, it would come out something like this type of problem. You'd get one number, you'd plug it back in and get the second number. So this is not a one solution problem. What is it? Yeah, this is infinitely many solutions. Or you could also say the solution is all real numbers. Any number that you pick would be a solution, because these are the same equation. Okay, these are the same line, so they cross at infinitely many points. So any point that's on the first line is automatically on the second. Automatic. Okay, any questions on that? All right, so let's try elimination with 3 variables. Okay, so with 3 variables, basically the goal is going to be, you're going to pick one equation. You're going to use that equation to get rid of the same letter in 2 other equations. Right? So you can pick an equation. Let's say you pick the first equation. And let's say you want to get rid of x. So you're going to take the first equation, multiply it by something, add it to the second, so you cancel out your x's. You're going to take the first equation again, multiply it by something, add it to the third equation, so you get rid of your x's. So when you're done this step, all you're going to have left in the second and third equations would be y and z. then it's going to be like a problem we just did. You have two equations with two letters, and you'll finish it up. Okay, so that's basically what I just said. Right, so we'll be doing a lot of substituting. Once you get one answer, you'll substitute back into other equations to get all your other answers. All right, so let's look at this with a problem. Okay, so there's our system. The variables are x, y, and z. Generally, you want to try to pick a variable to eliminate that has a coefficient of 1. That's going to be the equation we use to get rid of the variables in the other equations. You could do -1 as well, but 1 is even easier because it's positive. What equation there has a variable somewhere in it with a coefficient of 1? James? The third one. So the third equation is what we're going to use to try to get rid of some variables. What variable has a coefficient of 1? X. Okay, so my goal is I'm going to use equation 3. I'm going to multiply it by something, and I'm going to add it to the first one to try to get rid of the x. Then I'm going to take equation 3 again, multiply by something different, add it to the second one to try to get rid of the x. So when I'm done, equations 1 and equation 2, the x's are going to be gone. And I'm just going to worry about the y's and z's, and I'll repeat it. I'll get rid of another variable. Okay, so now we've got to figure out what we're going to multiply by. What could you multiply equation 3 by so that you could add it to equation 1 to cancel out the x's? Joe?
-2.
Yeah, let's do that. We're going to take equation 3, multiply it by -2, and we're going to add it to the first equation. Okay, I'll do that in 2 steps. Some people do it all in 1 step, but let's do it in 2. -2 times the third equation. Okay, just make sure you check my signs, make sure we're good. Okay, and we're going to add it to the first equation. Okay, when we add them up, we're going to get a new equation, but the new equation is just going to have y and z in it. Okay, Brianna, what's my y term going to be? So we got -5y. Okay, Colby, my z term?
5z.
So we got +5z. And then 16 plus -1 is 15. Okay, I'm going to put a box around it. We're going to come back to this equation in a little bit. Let's call this equation 4. Okay, now we're going to do the same idea again. Take equation 3. What could we multiply equation 3 by this time so that when we add it to equation 2, we'll make the x's disappear? Augustine?
3.
Well, if you multiply the bottom one by 3, you'd have a 3 and a 3, so they wouldn't cancel.
-3.
Yeah, let's multiply by -3. So take the third equation, multiply by -3, add it to the second equation. Okay, so -3 times the third equation. -3x minus 12y plus 9z equals 24. Add that to the second. 3x minus 2y plus 2z equals 15. Sometimes you get lucky and 2 letters cancel out at the same time. That doesn't happen here. All right, so we get -14y. 9 plus 2 is 11. Z. 24 plus 15 is 39. Okay, we'll call that one equation 5. Okay, we're done with working with equations 1, 2, and 3 for now. We're just going to work with equations 4 and 5 because it's 2 letters, 2 equations. Okay, so we took it from 3 letters with 3 equations down 1 step. 2 letters to 2 equations. All right, so it'd be nice if we could just multiply one equation by something, but I think we're going to have to multiply both. Okay. I would probably try to make the z's cancel out. I think, unless you can find a common factor that 14 and 5 both divide into, that's smaller than 14 times 5. Okay. So what could we do? What could we multiply equation 4 by, and then what could we multiply equation 5 by? If you want to make the y's cancel out, you can go for that too. But.
4 by 11.
Okay, multiply equation 4 by 11. Okay, let's do that first. So you're going to get negative 55y plus 55z. And we have negative 15 times 11, negative 165. Okay, and Darren, what do you want to multiply the bottom one by? Or equation 5, sorry. Negative 5. Okay, let's try it. So we've got 14 negative times negative 5 should be 70. I just must have forgot my negative. Okay, so negative times negative, that's positive. Negative 5 times negative 11 is negative 55z. Okay, I like that. That's good. And then the last part, 39 times negative 5. Negative 195. Okay, negative 55 plus 70.
The ending one.
Oh, should be,
Should be a positive 165.
let's see. On the first one we did?
Yeah.
Okay, so everything looks right on the bottom one. Let's check that. That should be positive, negative, negative. Yep. So that one's good. But the top one, let's see. Multiplied everything. Should be negative, positive.
Oh, that's equation 5.
The equation 4,
Yeah, equation 4.
it should be positive. 165 should be positive.
Yep. Because we multiplied by 4. So that first one should stay negative. The second one should stay positive. The last one should also stay positive. Thank you. So luckily we caught that before we actually did anything. So just erase the negative. Thank you. Okay. Any question on why that's positive? It's just 11 times 15. I don't know why we wrote negative. Okay, everyone agrees with everything else we have though? Okay. All right, now add these up. What's 70 take away 55? James? 15. Z's are gone. And then we have 165 minus 195, negative 30. Okay, so what's y? Is it 2? Or negative 2? Yeah, negative 2. Okay, you don't always have to get integers, but I picked this problem to have nice answers. So, okay, so y is negative 2. Okay, next step. Now you're just going to go back and substitute. Pick either equation 4 or 5. Let's do 4. Numbers look smaller. Plug in negative 2 for y in equation 4. So you're going to have negative 5 times negative 2 plus 5z equals 15. It's going to give you 10 plus 5z equals 15. Bring the 10 to the other side. Z equals 1. Okay, so now we got 2 answers. Okay, for the last one, now we're going to go all the way back to one of the first equations. You can pick either equation 1, 2, or 3. Fill in y, fill in z. Let's just do the top one. So 2x plus 3y minus z. Okay, so 2x plus 3y minus z. What was that equal to? Negative 1. Yeah, let's solve it, see what we get. So 2x minus 6 minus 1 equals minus 1. Okay, negative 6 minus 1 is negative 7. Add 7 on both sides. And divide by 2. So x is 3. Again, if you wanted to write this as an ordered triple, you could. 3, negative 2, 1. Okay, any question on that one? So other than that minor mistake we made, which would have messed up the whole problem, we just had that extra negative, but luckily somebody caught it right away. So we're good. All right. Anybody feel like they need to do another one of that type, or we're okay? The only thing here, what would you want to fill in for y? Yeah. Well, if it's not there, if it was a 1y, I'd have to fill it in for you. But if it's not there, it's a, yeah, 0y. So what I would do is use this to my advantage. I already have a 0 for y. Why don't I try to get a 0 for y somewhere else? Maybe multiply the top equation by 2 and add it to the third equation. That would cancel the y's out. Then I'd have 2 equations with the y's already gone. If you don't want to use this to help you, don't. Try to get zeros somewhere else, but that might be easier. Okay, another thing you could do, no, actually that would mess up y. I was trying to think of a way if I could get zeros in both spots right away and just have a variable by itself after one step. Not sure you can quite do that here. All right. So the next thing is basically a more efficient way to write everything we've been writing. All right, so if we have a system like that, okay, the way we're going to represent it tomorrow is with a matrix. Okay, when you use a matrix, all you're doing is writing the numbers. That's how you could represent the left-hand side of that equation. And that's the right-hand side. On the left, this is called a 2 by 2 matrix, 2 rows, 2 columns. This matrix is 2 rows, 1 column. And basically our goal, when we have a matrix, the goal is going to be to get 1s on the main diagonal and 0s below. I don't care what's above it. So that's going to be our goal, which is basically what we've been doing today. We're going to take one equation, we're going to multiply it by something so we can make something cancel out. So if you took this top row and you multiplied it by -3, and then you added it to the bottom row, you would get a 0 in that spot. That would be your first step. It's very, very similar to what we did today. If you had a 3 by 3 matrix, you'd be using that to solve a system with 3 variables. Our goal is going to be get 1s on the main diagonal and 0s everywhere below. I don't really care what's above. Okay, and by doing this, our last equation is just going to have 1 variable in it, and it's going to be equal to a number. Okay, and we'll know one of our variables. Then we can substitute it back into one of the other equations to get our next variable, and then back into the original. So tomorrow we're going to do everything we did today except with a matrix. Right, so I just want you to see it's a more efficient way of writing things. You don't have to write the letters. All right, and the last part. Let's look at a couple of the problems that Mr. Babb put up. He said particularly problem 3 would be helpful for calculus. Problem 2 is a little bit disappointing when we solve it because it's where an ellipse and a hyperbola, no, it's an ellipse and a parabola intersect. And I think it ends up being something like this. Parabola and ellipse. They don't intersect. So that's kind of sad. They don't intersect. So let's try number 1. And then I'll give you your homework. Okay, it says y equals x squared plus 2. And y equals negative 3x plus 4. Okay, can't use elimination here because we don't have all linear terms. Got to go with substitution. Well, what's nice is both equations are already solved for y. So let's start with this. Take that, plug it in right there. Okay, and I don't think this one's going to be too bad. X squared plus 2 equals negative 3x plus 4. Victoria, what kind of equation is that?
Quadratic.
Yeah, it's quadratic. Good. Highest exponent is a 2. What I would do is put everything on the left-hand side. So you get x squared plus 3x minus 2. And will that factor? We can try. Well, you need one term to be positive and you need one to be negative. So the only choices you have are 1 and 2. No matter how you try that, it's not going to work out. Okay, you can't factor it. So this would be something you'd use quadratic formula on. Okay, A is 1, B is 3, C is negative 2. Okay, we already went through a problem earlier today with the quadratic formula, so I'm not going to go through that part again. Does not factor. Okay, keep in mind the number of possibilities you could happen. You're trying to find where a parabola and a line cross. You might get 2, 1, or no solutions. Okay. The way you're going to know if you get none is if the radicand comes out imaginary and you take the square root, there's no solution. Okay. If it doesn't come out imaginary, you're going to have at least 1 or 2. All right, let's look at the third problem he put up. Okay, this one I haven't tried to do yet. Okay, it's y equals e to the 2x, and y equals x plus 4. Thoughts on this one? Yeah?
Instead of finding out what y is, can you, on the second equation, move the 4 over so that you find out what x is? And then when you find x, plug it into the variable, or plug it into the
Yeah, you
x
could.
element?
Yeah. So you want to solve this one for y? I'm not saying that's going to be easier or it's any kind of shortcut, but I mean, there's no reason why you can't do that. Right, so she said to get y by itself, so you have y equals x minus 4. I'm sorry, x equals y minus 4. And then plug that in. Okay, that's the easy part. We're still going to have a variable in the exponent, and we're going to have to deal with that somehow. So you get y equals e to the 2 times x. Okay, next part, still pretty simple. I would at least distribute out the 2. So now you have all one variable. Okay, any thoughts what you could do next? What is usually involved when you have a variable that's in your exponent? Like if I asked you to solve an equation like 2 to what power would give me 13? What thing in math do you end up using? Yeah? You can use a root when you have an exponent that's a number, and you have a base that's a variable, like x squared equals a number. You can take the square root of both sides, but you can't use a root here. Anyone remember what you do? This is a logarithm. Okay, the only way to solve when you have a variable in the exponent is to use a logarithm. Since we have e in this problem, using ln, okay, that might be a good idea. Okay, so let's take the natural log of both sides. So the natural log on the left, and the natural log on the right. Okay, look at the right-hand side. When you take the natural log of e to a power, okay, one of our properties of exponents we talked about, this whole part cancels out. Right, so all you're left with is the natural log of y equals two y minus 8. So at least we got rid of e, but now we have an ln. So. Any other thoughts on how we can solve that? I mean, I can get all the y's on the same side. That'd be pretty straightforward to do. I would, let's see. Could put all the y's either on the left or on the right. Let's put them on the left. Okay, how about from there? I have to call Mr. Babb. This is his problem. See anything you can try? Because I think I'm stuck at this point. I'm not sure. We haven't done anything wrong up to this step. Everything we've done has been fine. I'm just not sure we're going to be able to solve it. Let's
You take a different route towards it.
a root.
No, a different way. Like
There might be a different way. Maybe we went the wrong path here. Let's graph those just to even see if there is a solution. I think there is. So we got y equals, what's the first one? E to the 2x. Okay, that's an exponential. It's just going to curve up very quickly once it goes past the y-axis. And then you're graphing the line y equals x plus 4. So yeah, it's going to have a solution. It's going to cross in one spot. 2 spots, sorry. So it is solvable. Anybody have a thought on a different way?
Just have them equal each other.
All right, you could try setting them equal to each other rather than doing this substitution. All right, so we would just say x plus 4 equals e to the 2x. The problem I'm still going to have, though, is I got to get rid of this e. And the only way to do it is to take an ln of both sides. Because if you've got that variable in the exponent, you can't get the variable by itself. So if you do that, now you've got this. Now there are rules for logarithms, but not when you have a sum inside. Okay. If you had a product inside here, we could do something with it. If you had division inside here, we could also do something with it. Right, so I might have to take a look at that a little bit more myself or talk with Mr. Babb about how to solve it. Okay, there are some equations that you can't solve. I can think of one with a log that I know you can't do. Actually, a very simple equation. And I'm wondering if this is the type Mr. Babb gave us. I know you can't solve this equation. I've looked it up. Not with algebra. So if you basically compare this to what we have, e to a power, you've got a linear term plus a number. I don't think the problem he gave us can be solved with algebra. I don't think you can do it. I'll have to ask him if he thinks you can, but if this problem we have is basically this type right here, which it looks like it is, it's not solvable with algebra. So that's a little disappointing. But the methods, at least the methods we tried were correct. We tried substitution, we tried logarithms. You know, sometimes you try it, it doesn't work out. That's part of the process. Something to get used to.
Shucks.
All right. But hopefully, any questions on the first one? At least this one seemed to be working out. Alright, so homework tonight, it's mostly going to be solving linear systems, so you're not going to have to worry about the nonlinear ones. And it's page 541, 1 to 21 odd.